I will I will begin with a word of prayer. I guess it's time. Dear Father, we thank you for this day. Again, I thank you for this class. Just ask you to bless our work today, Lord. Help us to glorify you what we do and just to learn more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. So, let me begin with a calculation we did before, but this time I'll do it a little bit more fancy. It's a calculation worth repeating. So here it is. Here's the backdrop. The z minus z naught less than r less than rho. And we'll suppose that the modulus of w minus z naught is equal to r. All right, hence, what's that tell us? Well, that tells us that the quotient of z minus z naught against the modulus of w minus z naught, well, that would be less than 1. All right, so with that in mind, we can calculate this here quantity, f of z over w minus z. And so the game I'm going to play here is to try to rewrite this division by w minus z as a power series centered at z naught. And so this is a useful calculational trick that we will use, so that's why this is worth doing, if nothing else. And so how do you make that happen? Well, we do w minus, let's see here, minus z, and then we just subtract, well, we could add z naught and then subtract z naught, all right? That's just adding 0. And let's see, if you tilt your head and squint, you can see that that's nothing more than f of z over whale, w minus z naught, minus parentheses z minus z naught. Notice minus minus is a plus there. And then we know that the road to any kind of cool power series calculation is geometric series. Like everything is geometric series. So many things are geometric series, like seriously. Anyway, so this is f of z over w minus z naught. Factor that guy out. And if we do that, I am owing you guys a division by w minus z naught there, right? All right, great. Notice that the fraction that just appeared has a modulus which is less than 1 because the quotient of the moduli is the moduli of the quotient. And so lo and behold, we have the following formula. F of z over w minus z is equal to, what's it equal to? Well, it's equal to f of z over w minus z naught times the sum, n equals 0 to infinity, of z minus z naught over w minus z naught to the power n. All right, which of course we could clean up a bit. I'll leave it like that for the moment though. So then what we're going to do is simply integrate this thing. I guess I can, one more step. So this would be the same as the sum n equals 0 to infinity of like f of z times z minus z naught to the power n divided by w minus z naught to the power n plus 1. Great. So take this thing and integrate. We will integrate over the circle of radius r centered at z naught. So if we integrate this thing, modulus of w minus z naught equals to r. So put a dw up here. Likewise, all right. Just copying the same thing again here. W minus z naught equals to r. This thing dw. Then what happens? Then if we switch the order of integration and summation, right, which is actually justified, because of the uniform convergence of power series, right, which allows us to switch the order of integration and summation as we learned last class. And so what we got here is just straight up the summation n equals 0 to infinity of the integral of f of z dw over w minus z naught to the n plus 1, all of that times dw, right? And this is done over the circle of radius r centered at z naught. Okay? But on the flip side of things, let's see here. What else do I know? Oh, I know that this is also equal to, I mean, this is, you know, if you allow me this short Minga style calculation, this is equal to the integral over w minus z naught equals to r of f of z dw over w minus z, which is equal to what? Remember Cauchy's theorem? Cauchy's integral theorem, this is equal to f of z, so there you go. We have derived Cauchy's generalized integral theorem at z naught by applying the geometric series to Cauchy's integral theorem, right? And there's more than we can do because we still have, you know, we still have the fact that f of z is analytic, which means we can write this also by Taylor's theorem, sum n equals 0 to infinity of what? The nth derivative at z naught, right, over n factorial times z minus z naught to the power n, right? So, and remember then, it follows that this right here, right, has to be equal to that right there. And so what do we get? And I think I missed a, this is, I'm missing a 2 pi I factor. Where does it go? I guess if I don't put it here, it has to go over here, right? And if I put it there, rats. Well, I don't know. If I put it here, right, which is probably where I should put it, then this is actually, I'm missing a what? I'm missing a 2 pi I here, right? Logically. Anyway, so long story short, we have the following formula, right? The nth derivative at z naught over n factorial, it is equal to z integral, 2 pi I, right? 2 pi I integral modulus of w minus z naught equals to r f of z dw over w minus z naught to the n plus 1. Of course, this is the what? This is the generalized Cauchy integral formula, right? Now, what do we need for this calculation to hold? We need to know that f of z has to be holomorphic where? So like f of z needs to be holomorphic in here, right? On these, for this disk, that's the condition for the Cauchy integral formula, right? The f of z is holomorphic. The badness of the integral is just in the division, right? Yeah, Preston?
Are we not missing z minus z naught to the n next to our summation there? Right? We say 2 pi f of z equals that sum.
Oh, here? Oh, yeah. Thank you. Look, I've got an extra dw. But we don't need that. We need a what? Good grief. Thank you. My bad. Okay, I think we fixed it. So then what? Well, the rest of the theorem, and I'm you know, tracing out the remainder of theorem 8.42 in the notes on page 115 if you're keeping score here. So the rest of the theorem is that if f is bounded, then the nth derivative is also bounded. So like suppose that in addition we knew that, you know, f of z was like less than or equal to m, right? On you know, on the circle. I can't write down here. Okay, so like on the circle, suppose we have that bound, then we can apply the ML theorem, right? We take the modulus of this, take the modulus of that, right? And that's less than or equal to what? Well, 2 pi, right? Times what? Times the length of this, which is what? 2 pi r, right? It's a circle of radius r. And then what is this? Well, that's r to the n plus 1, right? And so what you got is m over r to the n plus 1. The number of 2 pi's I have there feels wrong. Well, I've neglected to put my 2 pi over here, right? There was a 2 pi over here, right? My bad. I'm sorry. I've cluttered things with multiplying this by 2 pi, you know? Okay, so anyway, that 2 pi cancels, and you just got what? The modulus of the nth derivative at z naught is bounded by what? Looks like m, if I'm not doing this wrong, n factorial, right? Divided by what? Looks like r to the n, yeah? And I still think I've got a 2 pi up there from the ML theorem, right? Yeah. Look what I've done. 2 pi m n factorial divided by r to the power n. And that's the claim of the theorem, is that there exists a constant. So that, in fact, the claim of the theorem was to put the n factorial over here, right? In fact, it's a k in the theorem, but the n factorial is over there. And that's the additional claim of the theorem, is that if the the function is holomorphic, then the nth derivative is bounded if the function's bounded. Yeah.
On the last line, like the last equation, where did the 2 pi I come from in front of the integer?
This one?
No, the one to the right there. Yeah,
That one.
Yeah.
Nonsense, isn't it? And in view of that nonsense,
So I think you have no 2
this is a nonsense.
bound, right?
That's nonsense. And then the 2 pi's cancel.
End up canceling each other.
Yeah, thank you. I'm sorry, guys. I got off track somewhere. I think it's fixed now. But the point is, this is an interesting thing because it says that if the function is bounded, then its nth derivatives are likewise bounded, according to this rule. Okay. I think I derived this the other day, and I called it what? Cauchy's estimate, I think it was, right? Alrighty then. So corollary. This is corollary 8.43. It says that if f of z and g of z are holomorphic for modulus of z minus z naught less than r. So if they're holomorphic on an open disk of radius r centered at z naught, and if the kth derivative at z naught is equal to the kth derivative of g at z naught, all right, for k greater than or equal to 0, then f of z is equal to g of z for modulus of z minus z naught less than r. In other words, if you have two functions which are holomorphic, all right, on some disk, and they agree with their values at the center of the disk, then they're the same function. All right. And so the proof is really just the generalized Cauchy integral formula, which is that what that theorem said is that if the function's holomorphic, then it's represented by its power series. Okay? So the proof is just, okay, so f of z and g of z are represented by the power series. We're assuming that the derivatives match at the center point, but these derivatives fix the coefficients of the power series, right? Because these divided by k factorial are the coefficients of the power series. Therefore, they have the same formula. Therefore, they're equal. That's the proof. Now, corollary to this is that, and we've said this before, but I'll just state it again, it's simply this. If f of z is analytic at z naught, all right, with f of z equals to the sum k equals 0 to infinity of, let's say, a sub k times z minus z naught to the power k, all right, then the radius of convergence of the power series is the largest number r such that f of z extends to be holomorphic. Let me draw a picture of this. So here's z naught, right? The radius of convergence for this power series will be as big as you can make it up until what happens?
It's not holomorphic at a point inside the circle.
Well, it says up until, it's the language I use in this is the radius of convergence of the power series is the largest number r such that f of z extends to be holomorphic on the disk. So extends to be holomorphic. So like I've defined f of z to start with. It's just defined where? The point, right? So then you can consider like an open disk, right? And remember we had the other theorem that if there's one point of convergence, then it converges normally inside that, right? So essentially what's going to happen is until you hit a singularity, right? If you hit a singularity, which is a point where it's not holomorphic, right? The radius of convergence is the biggest r that you can find until you hit a singularity in that. So let me see here if I have an example that helps with that. I mean, there was probably, more or less, that was like problem 19 in your take-home test, was this idea. I gave you a series to define the function, right? And then you figured out what's the largest set on which it's converging, right? And you found that you ran into a point where it didn't converge anymore, right? And that is exactly the radius of convergence, and that's the same place where the function that you're defining by a power series ceases to be holomorphic. So, all right, see here. So now, at this point in the notes, I define all of your favorite functions, cosh, sinh, exponential, all these things by power series, right? And so you guys know all that. We've talked about that before here. I'm actually going to skip past section 8.5 for a second. We'll come back to that later today. So what I want to talk about next is like manipulation of power series. So here's a theorem. If we have the sum over, let's say, ak z minus z naught to the k. I'm going to use n instead of k because my k's are horrible. Z to the n equals 0 to infinity. And if you've got the sum over, let's say, bn, z minus z naught to the n equals 0 to infinity. So these are two power series, right? And suppose that these are two convergent power series on a domain D. All right. I'm just going to go ahead and sort of combine two theorems in the notes. Number one, you can say that, you know, a constant times the first series, right? Plus the second series. You can add them, right? And what do you get? We just do what? We just add corresponding components, right? I should just write sum. So the sum of two convergent series is again a convergent series, and if you multiply by a number, you can just bring it in, right? And what else? 2, if we can define the product of two series, right? If I've got an z minus z naught to the n equals 0 to infinity, times the sum bn z minus z naught to the n equals 0 to infinity, well, that's equal to a convergent power series, let's say c sub n z minus z naught to the n equals 0 to infinity, all right? And how can I prove these assertions that, like, the sum of power series is, you know, again, a power series which is convergent? Like, the proofs are really easy in light of the theory that we have. See, because what I can do is I can just say, okay, I've got this function here, f of z, all right? I've got this function over here, g of z, right? They're holomorphic on the domain D, right? So that means then that I can form, for number one, to make this corollary more exciting, I really should show you some more exotic series where you run into like a natural boundary and things, but we'll get to that when we get to it. Sorry about that. So like for one here, I should just consider h of z equal to what? For the proof of number one, just consider h of z equals to c times f of z plus g of z, right? Is that holomorphic? Sure is, right? So that means that h of z has a power series, right? But the corollary we have right there says that the power series is determined by its kth derivative. So I just differentiate this, right? Differentiating at k times, what do you got? Like the kth derivative, or I'll use the nth. The nth derivative at z naught for h is equal to what? C times the nth derivative at z naught for f plus the nth derivative at g, like that, right? And of course, if I just, you know, divide by n factorial here, this is literally what? C times a sub n plus b sub n. Because that's the meaning of the coefficient in the power series, right? It's by Taylor's theorem, the meaning of a sub n is the nth derivative of f evaluated at the center point of the series divided by n factorial, right? So by the theory that we've worked out already, in Taylor's theorem, we could call it that. That's what this is. This is a sub n times that c, right? This is b sub n. And this over here is what? It's the coefficient for the nth term in the resulting function h of z, which is what I've written over here. See? And that proves one. Because two power series are determined by their coefficients. Okay? What's the proof of 2 look like? Ooh. So proof of 2 is where I realized that I probably missed out on an opportunity for a homework problem. All right? Because this time we want to define h of z to be what? We want our h of z, the function, the new function we're defining, it's the product. See, it's the product of f of z and g of z, isn't it? Now differentiating this k-fold, differentiating this n-fold times, that was a piece of cake. Differentiating this n-fold times requires a little bit more nuance. So like h prime of z is what? Well, it's f prime of z times g of z, right? Plus f of z, g prime of z. What's f prime prime? What's h prime prime? Well, it's f prime prime of z times g of z, right? Plus 2 f prime of z, g prime of z, plus f of z, g prime 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 of z. No, just 2 primes. Double prime. And a third time, h prime 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 of z is f triple prime of z times g of z, plus 3 f prime prime of z, g prime of z, plus 3 f prime of z, g prime prime of z, plus f of z, g triple prime of z. Because, well, you guys know this. These are just the product rule for the second derivative, the product rule for the third derivative, right? You remember this from calculus? No, not really. I mean, if I'm feeling particularly nefarious, maybe I'll teach this in Calc 1 next semester. There is a stone-cold formula for this. This is Leibniz rule for the product. There is a formula for this. Here it is. So the derivative, and this is what I should have made a homework problem, guys, but I lost my chance. FF, that's not what I want. FG, and I'll stick with my notation here because otherwise I'll get into trouble. The kth derivative of it at z naught. It turns out you can write that as the sum I plus j equals to k factorial over I factorial, j factorial, the ith derivative of f, oh yowzers, I didn't want a z naught there, just of z, the jth derivative of g at z. All right. And what this actually works out to, as you guys were mentioning, it's the Pascal's triangle, isn't it? Yeah. So that's the combinatorial pattern here. So like the next one is k, the k minus 1th derivative at z, g of z. Eventually we get to k times just one derivative of f, and k minus 1-fold derivatives of g. And then finally, last but not least, f of z, 0th derivative, times the kth derivative of z. All right. So there it is. Now this is pretty cool though, because this shows you how to define the product of series. Do you see that? Because we know that the product of two series is a series again. This means that the rule for multiplying series is derived from this calculus. See, because the rule for multiplying series follows then from Leibniz product rule. See, because the formula for C sub k is what? It's the what? It's the fg, it's the kth derivative of that, right? Divided by k factorial. Right? But I'm supposed to evaluate this where? At z naught. So what happens, right? What happens is that this becomes the sum I plus j equals to k. Notice that the k factorials, they be canceling. And you just got like the ith derivative at z naught over I factorial times the what? The jth derivative at z naught over j factorial. But what are these? Well, that's exactly what I've denoted as, you know, a and b, the coefficients of the series. So this is nothing more than like the sum I plus j equals to k of a sub I, b sub j. This is the rule for the Cauchy product, two series. We just look at all possible ways to like add up to get the same degree. For example, did I do it? I guess it's my first example, isn't it? Well, that was kind of an example. Fine, I'll call it example 1. If you guys want to multiply, for instance, suppose you want to multiply 1 minus z, no, excuse me, 1 plus z squared plus z cubed plus dot 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 dot, right? Times 1 minus z, what do you get? Let's see here. So we have to do it order by order. What are the constant terms? How can you get a constant here? These two, right? That's it for the constant. How about z's? What do I got? I've got 1 times that gives me minus 1, right? Z times that gives me plus 1. How about my z squareds? Z squareds, I've got 1 here, right? And I've also got that times that gives me minus 1. And this continues, so this simplifies to just what? These two things multiplied just to give me 1. Is this surprising? Not really. Why? What is this? Do you guys know?
It's the,
What does that converge to? It's the what?
the standard geometric series.
Right, this is the standard geometric series. This converges to 1 over 1 minus z. So shockingly, 1 over 1 minus z times 1 minus z equals to 1. This is not surprising, right? This is a stupid example. Let me give you an example which actually does the Cauchy product more interestingly. How about this? What if we try example 2? What if we try multiplying, let's say, 1 plus 2z plus 1/2, well, let's say 2z squared plus 1/6, well, excuse me, 4/3. My bad. Fine, I'll show my handiwork. 8/6 z cubed plus dot 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 dot. I'm gonna multiply that by, oh, I don't know. Let us say 1 plus 3z plus 1/2, 9/2 rather, z squared plus, oh, I don't know, 27/6 z cubed plus dot 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 dot. What happens when we multiply these series? Let's work it out. What's the constant term? 1. All right. What's the term linear in z?
2z times 1, 3z times 1.
So I get what? I get 2. I get 2 plus 3, right? How about z squared? How many z squareds do I got? Let's see here. Let me color code that for you guys. So to get z squared, we can either do 1 times that, right? Or we can do 2 times that. Or we can do this guy times that. Those are 3 choices, right? So we've either got a 9/2 or a 6, or what? 2? Correct? All right, I'm running out of boards. I'm just going to write plus dot 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 here. And what do we got? We've got 1 plus 5z plus 1/2 of 5z squared Now, I say that's 1/2 of 5z squared because if you look at this, this is 12, no, that's 8, which is 16. 16 plus 9 is 25. 25 over 2 is 5 squared over 2, right? So, as advertised. What's the next thing I haven't written? Do you guys recognize my...
Third times
Ooh, I take your 3 and I raise you a factorial. 1 over 3 factorial times what?
5z squared.
5z cubed. Cubed.
See, I meant those things.
You meant those things. Very good. So what am I up to here? What game am I playing this time? Stupid calculation. What is this? Do you recognize what's going on here? Can you see the man behind the curtain?
It's a series with
What series am I using?
5z.
Yeah, that's e to the 5z. And why is that e to the 5z? What did I do? This is so stupid, right? Look, this is exactly e to the 2z. This right here is e to the 3z. So it should not be surprising to us that this is e to the 5z. Because e to the 2z times e to the 3z is e to the 2 plus 3, 5z. Eh? Did I do something wrong?
I didn't know that e to the z could be derived like that.
In fact, yes, we can prove through series arguments that e to the x times e to the y, where x and y are complex numbers, is actually e to the x plus y. That's actually not a bad homework problem. Since you asked for it, I will put it on the next one.
Okay.
The way to do that is to just, it's very simple actually. It's literally just this, the Cauchy, the definition of the product, like the Cauchy product, paired with the binomial theorem. It's just those two things put together give you this. It's just that. So, and that would be good for any math major or engineer to work through. Anyway, shall we work another? So I wanted to just spend some class time just calculating series because, you know, it's been a little bit since Calc 2. I guess we don't do series in Calc 1, right? You're like, what is this, Russia? I don't know if that, I don't think that Russia even exists anymore. But, I probably went to grad school with the last vestiges of that system. I still had some like fellow grad students who had been produced by elite Russian schools. Those students, those students were formidable. I tell you. Okay, so here's another one. How would you find example, let's see, what am I on? Example 3. I spend a little bit more class time on calculation of series and then we'll get back to the theory, okay guys? That's the plan here for today. Let me make sure I hit all the high points I need to hit here. Yeah, okay. So what if you wanted to, I don't think we talked at all about division of series yet, but how would you do that? Like, for example, suppose I want to find the power series centered at 0 for 1 over cosine z. Let me show you a sneaky trick for this. All right? So the uninspired way of doing this would just be to just do what? Be like, f of z is secant z, and I'm just going to differentiate it n times. I strongly recommend not doing that, right? So instead, how about this? We know the power series for cosine is what? 1 minus 1/2 z squared, right? Plus 1 over 4 factorial z to the 4th, and so forth and so on, right? Minus 1 over 6 factorial z to the 6th. I don't know why I'm going so far, but anyway, there we go. Enough. So what we could do, right, is just make a substitution. See? This you can all think of this as, oh, I don't know, W. And what is this? Well, by the geometric series, this is 1 plus, well, W plus W squared plus dot, 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 dot. And that's a pretty good strategy here because you see, that's 1 plus what? 1/2 Z squared plus 1 over 4 factorial, excuse me, minus 1 over 4. I gotta mind the minuses, right? I guess it's plus 1 over 6 factorial, Z to the 6th plus dot, 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 right? That's my W. And then plus that same stuff, right? Squared. So you guys tell me, what is the power series then? Well, I can tell you this much. It starts with a 1, right? And how about 1/2 Z squared? Is there any other quadratic term? Is there any other quadratic term to be found in all this? What is this? Right? Whatever that is, 720, I guess. I don't know. Check it out, right? This is what? Order at least what?
4.
At least 4. This has order at least 2, right? What's the next thing? The cube, when you get to the W cubed, right? That's got what? At least 6, right? So if I just want to calculate to order 4, I can just look at what I've got here already, and that's enough. So like to order 4, I have, plus, I'll put some parentheses here, Z to the 4th. I've got a minus 1 over 24 from this 4 factorial here. But then what do I get from over here? How do I get a Z to the 4th? It's from this times itself. So 1/2 times 1/2 is 1/4. It wouldn't be too much work to continue this a few more orders, but I think I've illustrated my point, right? So up to order 4, we have the following power series for the reciprocal of cosine. That's 6 plus 5/24, yeah? There it is. Okay, now that we've done this, what's the power series for tangent? Centered at 0. How would you do tangent in light of this? We could do what? We could do sine z, right? Times 1 over cosine, right? We could do that. If we wanted to find the power series for tangent, that'd be fun. What was the sine of z? It was what? It was z minus 1/6 z cubed plus higher order stuff. We're only going to go to like order 4 here, okay? And I got 1 plus 1/2 z squared plus 5 over 24 z to the 4th, like that. And so I use the Cauchy product again, right? I just collect like terms. So like what's the lowest order term? Lowest order. I always go order by order, lowest to highest, okay? What's the lowest order term? I think it's just the z times 1, right? So I've got a z. And then what's up next? What do we expect here? Think about this. Tangent of z is an odd function. We proved before odd functions have odd power series. Even functions have even power series. Not an accident that we only had even powers up here, right? Because 1 over cosine is 1 over an even function, which is in fact an even function, right? Even powers, even power. Now here, so the next is cubed because there is no square, right? There is no square. But the cube, what do we got? 1/2, right? Minus 1/6. Can I go higher? I guess I can go higher if I just, let me just do a little bit more because I think we can do it. We can do it, I think we can get it I think we can get to fifth order, even though we've only done to fourth order with cosine, one of our cosine. Isn't that funny? See how that works? I think that's kind of funny sometimes. You can get higher order with lower order data when it stacks up right. So like, what's z to the fifth? Do I have everything in the z to the fifth story? I think I have everything. See, because the z times z to the fourth gives me, that's one of the z to the fifth terms. So I get a 5/24. And then, let's see here, z cubed times z squared, that gives me a minus 1/12. Right? And what else? The plus 1 over 120. And what's that all work out to? Well, you got yourself a z. I believe that is 1/3 plus 1/3 z cubed. And what's that work out to? 2/15? Cool. Thank you. That sounds right. And so there you go. That's the first 3 terms in the power series for tangent, which is nothing particularly pretty, but we can certainly calculate more coefficients if we need to, right? So just wanted to remind you guys, this isn't really a reminder, I'm showing you some kind of like weird tricks for calculating power series, right? There's also much more pedestrian things like long division. We can do long division of series as well. That's another technique. Would you guys like me to review it, or does it not? You guys good on that?
Couldn't hurt.
Couldn't hurt, okay. Let's see here. Let's find, where am I? Example 5. So let's see here. How about we will, oh man, I'm just drawing a blank on an interesting example here. I guess I can do the reciprocal of sine, if that's interesting. So like, let's find 1 over sine z. Well, I've done too much sine and cosine. Let's do sinh. All right. So here, I'm going to be dividing 1, right? It's kind of stupid. No, that's not what I'm doing. Stink. Sorry, guys. Drawing a blank here. Let me find my notes.
How many times does sinh go in 1?
Well, just a second. I had an example in here. Oh, yeah, I'm not going to be able to do that. Well, anyway, if you look at, let me just save us the trouble of it. If you look on page 123, I have an example of how to, I show exactly this example 4, but with long division. So you can look at that. So let me move on here. I need to make another definition. You're like, another definition? Yes. This one is interesting. Well, I mean, I think they're all interesting, but this one is especially interesting for to my taste. Let f be analytic, not identically 0 at near z equals to z naught, okay? Then we define, all right, a 0 of order n if the following. If we have f of z naught equals to 0, f prime of z naught equals to 0, on down the line, the n minus 1th derivative, big N, big N minus 1, derivative of z naught not equal to 0, and yet the nth derivative at z naught is not equal to 0. That's a 0 of order n. Okay, so if you have n equals to 1, it's called a simple 0. If you have n equals to 2, it's called a double 0. Okay? Yeah. And so I need to give us another I mean, we're going to look at examples of this in just a second, but I need a little more language here. Definition, z naught, an element of U, is called isolated. We may have talked about this before, but isolated point of U if what? If there exists some row greater than 0, such that if we look at the set of z and u such that the distance from z minus z naught is less than rho, we just get what? Fill in the curly brackets for me. What do you got there? So it's isolated, right? That means that the only point that satisfies this condition in U is just z naught. It's an isolated point, okay? So what I want to explain to you guys in the next few minutes of class is that the zeros of an analytic function, which is not identically 0, okay, and not identically 0 analytic function, the zeros are in fact isolated. This is very interesting, actually, for reasons we'll appreciate by the end of this section. Now, so you guys tell me, what does all this data mean about the formula for a function that has a 0 of order n? Can you guys tell me what that looks like then? What is it? No? Okay. So if I have f of z, if I have a 0 of order n, right? I have f of z is what? The sum, let's say k equals 0 to infinity, right? Of the kth derivative at z naught over k factorial times z minus z naught to the power k. So what does that simplify to? If it's got a 0 of order n, those are all 0 up until what? Up until n.
Oh, so it's equal to the series into k.
Right, we start at n. Everything before that's 0. So if we write that out in gory detail, you've got something like, the nth derivative at z naught over, big N factorial times z minus z naught to the power n, and then plus, I don't really care, let me just call it c2 times z minus z naught to the n plus 1 plus dot 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 dot. All right? My point to you is that if this is the situation, what can you do? You've got a z to the n everywhere here, right? You can factor out z minus z naught to the power n, all right? And then what do you got left over? Well, you've got the nth derivative at z naught over n factorial. And I suppose the next term would be what? It would be the n plus 1th derivative at z naught divided by what? N plus 1 factorial times z minus z naught plus dot 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 dot. Okay? This is just from the definition and the fact that it's analytic, which means it has a power series expansion, right? So, give this thing a name. Tell me what you notice about this function right here, if we call this h of z. What can you tell me about h of z? First of all, it's analytic, right? It's got a power series expansion. It converges because f converges. You can think about that. What can you tell me about h of z naught?
Oh, it looks like they all have a power series expansion.
Well, but h of z naught, this is 0, everything is 0 except for what? Except for the first term, right? If you plug in z naught into the formula for h of z, everything drops down to nothing except for the first term. But the first term by assumption is what? F the nth derivative over big N factorial. That's not equal to 0, right? So this h of z is not equal to 0 at the center point. So whatever's making the function 0 at z naught, it's all wrapped up into this initial factor right here, okay? And this, by the way, what I'm currently doing, well, I mean, this is the, well, let me just project it here at this point because I have a few nice formulas I should show you. But I have almost here derived what's called the factor. You know, you guys know the factor theorem. Remember the factor theorem from like college algebra or high school algebra or algebra? You remember the factor theorem? For a polynomial, you have x minus c as a factor if and only if what? Yeah, if c is a 0, right? If we're working in the complex domain. Well, what we're now looking at is the factor theorem for a power series. You see, we have, if I can find it. Oh man, that was poor planning on my part. Sorry. All right, I'll find it. So the cool thing is, if we look at a power series, we can pretty much see from it if the place the series is centered, if it's a 0 or not. Because, let's see here. So that's the calculation I was just doing, okay? But so we've essentially proved the factor theorem for power series. If f of z is an analytic function with a 0 of order n, then you can factor out z minus z naught. It's all good, I'm just adjusting. You can factor out z minus z naught to the n like that, times a cofactor h of z, which is another power series, which is non-zero at the point. Okay? It's pretty cool. It's actually incredibly useful, theoretically speaking. Now here's a, don't say I didn't give you an example. Here's one. If we look at z minus z naught to the n, that is a 0 of order n. Okay, that's the prototypical power function. If you differentiate this n-fold time, what happens? You just get what? N factorial, right? So, but before that, it's 0 when you plug in z naught. So that's 0 of order n. Sine of z squared. So like these kind of problems, what you want to do is use the known Maclaurin series for sine substituted in. And when you do that, you look at this and you go, oh, wait a minute, I can factor out a z squared. All right, this is actually an